Okay, thank you for invitation to this nice conference. So I'm going to talk about non-commutative version of our work with Boris Feigin. So main point is to construct non-commutative Poisson structures on projective spaces. It turns out that for non-commutative case it's not possible, or at least in some cases we can prove that it's not possible to construct elliptic Poisson structures on affine space, only on projective, which I will explain later. So this is a joint project with Vladimir Sokolov from Landau Institute in Moscow, Russia. And it is based on non-commutative differential geometry, which Maxim introduced long ago in his famous paper, Formal Non-Commutative Symplectic Geometry, which was written in 19th, I guess. 92. Yeah. And so it is very well written paper. I was able to read it without help of Maxim. Just I read it and learned this theory by myself. It was a very nice experience. And what I'm going to say, elliptic. So what we have done with Vladimir Sokolov, we constructed elliptic, some concrete examples, family of elliptic Poisson structures. And this was based also on my activity with another Russian mathematician, Boris Feigin. So something which is called elliptic algebras. We had a lot of papers. And so let me do the following. So first of all, let me assume for a moment that everybody here are familiar with Maxim's framework of non-commutative differential geometry, and I just formulate our result. Okay, and after that, I will try to explain this formalism for those who don't remember it very well. Okay, so first, let me recall what is elliptic Poisson structures in usual commutative case, which we found with Boris Feigin. So this structure is called Q and K tau. Tau is a modular parameter from upper half plane, and n and k are two numbers such that k is from 1 to n minus 1, and k should be coprime. The simplest case turns out is k is equal to 1. And then for xi are variables, so it's good to say that xi, where I belong to z by nz, there is such Poisson structure. So claim is this formula defines Poisson structure, usual Poisson structure on affine space, on n-dimensional affine space, where theta are, so you have something like theta I of z, where also I is z by n z, is a certain basis. This is a certain basis in the space of theta functions of order n. If you want, you can call it theta functions with characteristics. It is one of standard bases. I don't think that I should kind of introduce it in details. You can, if you don't remember it, you can read up, for example, in any of my paper on elliptic algebras, including our paper with Sokolov.
You get these numbers, theta of 0 and theta.
Yeah, these are theta constants. I have theta of 0 and theta prime of 0.
And they satisfy some algebraic equations?
Yes, they satisfy some equations, but I would prefer not to go to such technicalities. So about this, it's a good reference. Of course, it's classical thing. It's not our invention, but all notations which I use here can be found in any of elliptic paper of myself with Asa Feigin, or myself, or Vladimir Sokolov.
So what is the Q and K of tau, and how is it connected to the next thing?
Because here I omit arguments. This set of functions, they actually functions in two variables, which, sorry,
But what is Q of tau?
Yeah, it is a notation for this Poisson algebra. Poisson bracket or Poisson algebra. So I have polynomial ring with n generators, xi, with this Poisson bracket. And this structure we denoted by Q and K tau.
And tau is in the upper half plane.
And tau is a modular parameter.
And what is the sum over I not equal 0 and j?
J minus I. R should not be 0 or j minus I because, well, let me say one thing. Theta 0 of 0 is equal to 0. Good to know. And theta prime of 0 is not 0. Okay? So this case when I is either 0 or, oops, mistake. This is a mistake. If I is not either 0 or j minus I need to treat it separately. In this case, I have just xi, xj. And this term is written here separately. Okay, yeah.
Is it a generalization of square structure?
Yes, yes, yes. I should say that, first of all, with Boris Feigin, we studied quantum version of this. Algebras which are flat deformations of polynomial ring in class of non-commutative, associative, graded algebras. And this is quasi-classical limit. And if n is equal to 4 and k is equal to 1, this is only possibility in this case, then this algebra in different notations was introduced by Sklyanin in his famous papers on XYZ model. And if n is equal to 3, this algebra is a quasi-classical limit of family of algebras which were introduced by Artin and Tate long ago. And I guess that for n larger than 3, it is our result. For example, larger than 4, sorry. For example, if n is equal to 5, I believe it was our result. Okay?
So you say it's always the limit of some non-commutative?
Yeah, there is a family, well, let me write it here. Q, in our notations, Qn, k, tau, eta. If eta is equal to 0, it is a polynomial ring with n variables. When eta is not 0, it has the same dimension of graded components as polynomial ring in n variables, but it is no longer commutative. So in language of mathematical physics, it's called quantization. And in quasi-classical limit, if eta is close to 0,
Algebra is quadratic.
Quadratic, yeah, it is algebra with quadratic relations. It is a quasi-classical limit of these relations is this. Okay?
Okay, so the commutator divided by eta tends to this.
Yes, yes, that's right. I fix modular parameter, and this is actually point on elliptic curve. If it tends to 0, it tends to just commutative ring, and commutator tends to this. Tends to this multiplied by eta, to be precise, but I omit eta. Yeah? Okay, other questions? Well, such a nice family of elliptic Poisson structures. Elliptic because it depends on kind of modular functions or something like this. Well, I should say also maybe it's if k is equal to n minus 1, in this case, this is equal to 0. One can check identically. So it is trivial if k is equal to n minus 1. Okay? Now let me state non-commutative version of this. Okay, so again, let me just to summarize. This is a Poisson structure on affine space in variables xn, n variables. Well, let me go here. Well, now I assume that people know Maxim's framework, which I will explain, of course, when I finish with this formulation of this result. I decide to start with this because otherwise I will not come to this by experience. So this formula defines something which is called non-commutative Poisson bracket. In this case, in the case of non-commutative Poisson brackets, we cannot define just Poisson brackets of generators. We must define it for arbitrary non-commutative polynomials. And the formula is this. So here I have C I minus J R at some structure constants. Yeah, this is non-commutative. There is something which is called partial derivative of non-commutative polynomial, which I will explain. It's, yeah. And this is not commutative. I cannot swap I must write it in this order. But since I have this trace, which I will explain again, but trace has usual property that I can make cyclic permutations under trace. But I cannot swap anything.
So all the cyclic group acting on.
Yeah, I can swap this x r j plus r in the beginning. For example.
No, but you can see the special form when all.
Yeah, cyclic group acts the same as here. Here, not only cyclic group, it is actually Heisenberg group.
But with those who read Maxim's paper, this F and G are cyclic words, and this is also a cyclic word.
Yeah, it is because I have trace. I will explain this. Yeah, F and G are cyclic words, and trace. This is something from free algebra, but when I make trace, which I will explain. Now I assume that everybody knows this. Then this is also a cyclic word. And it is not enough to compute this for xi, xj. It's not enough information, so I must write this for arbitrary f and g. Okay? Well, so and for C structure constants, I write here formulas. They are very close to, rather coincide with formulas.
There's special hooks.
Yeah. I just want people to compare. Formulas are very, very similar.
And usual Poisson brackets have some property.
Yeah, yes, it also has some property, yeah.
And so this gives rise to Poisson bracket on matrices. So were they known before these brackets?
I don't think so, but to be precise, not on matrices, on something which is a quotient.
Up to conjugation.
Yes, up to conjugation, but in this case, let me, well, it's a very good question, the matrices up to conjugation, but in this case, I don't claim that this gives me non-commutative Poisson brackets on affine space. It is not a Poisson bracket on affine space. It is only Poisson bracket on projective space. I will explain the subtlety in a moment. Just want to emphasize that this is not non-commutative Poisson bracket on affine space, and probably I believe that there is no such Poisson bracket. At least for small n, we tried to find, and I'm not sure that this is a theorem, but highly likely that there is no. But there are Poisson bracket on corresponding projective space. Okay, it's a kind of subtlety. I will explain it in a moment.
What is the algebra of non-commutative polynomial? Is it just associative algebra?
Yes, free associative algebra, but I am going to, after we finish with this, I will explain in details. Strictly speaking, it will be my understanding of Maxim's framework. I will explain this in details when we finish with new results. Okay? And this, so if you compare, these formulas are very, very similar to this. But this is much more robust. You see, you cannot, here you cannot swap and then collect. It's not possible. Yeah, so for example, here you can collect. Here you can collect two terms. Yeah, because they commute. Yeah, but here you cannot collect.
C, I, J here are what?
What написано?
It is from Z by NZ. No. C, I, yeah.
Only this?
Only this, yeah.
Yeah. It's very similar to this, actually. Even this, what I write here as coefficients at xi, xj is actually sum this plus this, as you can see. So in some sense, set of these structure constants is equal to set of this structure.
So in other words, for 1 by 1 matrices, you will recover.
Yeah, for 1 by 1, I will recover this. So for 1 by 1, of course, it will be Poisson structure on affine space, but for n larger than 1, it will not be Poisson structure on affine space. So let me explain the subtlety now. Any questions? Any more questions about this? Let me explain the subtlety that, as I told, this is not Poisson structure on affine, but it is a Poisson structure on projective. So let me consider, I can do it here. Let's consider commutative. Let me explain this in commutative case where everything is clear, yeah? Because in non-commutative it is very similar. So in commutative case, suppose that I want to have a Poisson structure on projective space, but I want to write it in homogeneous coordinates. So let me write in this case the formula, so more general formula for commutative. Now it is commutative Poisson structure. It is something like, I have R, some structure constant, so I write some general case. I, J, K, I, so I have X, K, X, K, L, yeah, K, L, X, K, X, L, df by d, yes, xi, dg by d, xj. So this R, I, J, K, L are some constants. Suppose that I have such B vector. At the moment, I don't claim that it is a Poisson structure. I have such B vector for arbitrary functions. I have this. And of course, it is sum of by I, J, K, and L. Now, let's imagine that my aim is to construct Poisson structure on projective space, which means that I'm not going to apply this formula to arbitrary functions. I'm going to apply this formula only to homogeneous functions, to functions like this, f of x1 over xn, dot, 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 xn minus 1 over xn. And similarly for j. Suppose that I don't want to apply it for arbitrary functions, only to homogeneous functions. In this case, I don't have this kind of unique writing. Because for such functions, for homogeneous functions, I have the following identity. For homogeneous functions, f and g, I have such identity. Both is equal to 0. Which means that if I only care about projective space and Poisson structure on projective space, I can modify this formula by using this and this. For example, I can find x1 by df by dx1 and change it using this formula. Yeah? So in this case, this writing is not unique. It is given modular ideal generated by these two equations. Okay? If I care only about Poisson structures on projective space. Moreover, when I check Jacobi identity, so I should write f, g, h, dot, 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 it should be equal to 0. But it should not be equal to 0 on the nose. It should be equal to 0 also modulo this, and one more, which is so Jacobi identity doesn't need to be just equal to 0. It should be equal to 0 modulo these three identities. So if I have this, in terms of homogeneous coordinates, if I want to define Poisson structure on projective space and don't care about affine case, I should write this two-vector field. But this left-hand side is not unique and can be defined using these identities. And I require Jacobi identity also modulo this identity for f, g, and h. OK? Is that clear? Questions? Yeah? Well, in the commutative case, just a remark which actually doesn't have not a lot to do with this talk, but it might be interesting by itself, that in commutative case, there is a deep result and non-trivial result by Bondal and Polishchuk, that actually if you have such thing, if you have Poisson structure on projective space, you can always lift it to Poisson structure on affine space. You can always choose representative of this formula, yeah, such that Jacobi identity is equal to 0, not modulo these identities, but just equal to 0. And this is not correct in non-commutative case.
But to what extent this lift is unique in commutative case?
I'm not sure. So Bondal just proved that it exists as far as I know, and Polishchuk found some explicit formula for a representative, for a lifting. But I'm not sure that it is unique, yeah?
It's not unique, but there is some canonical representative.
Yeah, there is canonical representative as far as I know, found by Polishchuk. Yeah. There is explicit formula for lifting. It is not easy to guess, I think. It's some non-trivial result. But this doesn't have a lot to do with my talk, because for non-commutative case, it is not correct, simply. Okay? So this is about new results. And now, if you don't have questions about this, let me make a review about Maxim. And of course, other people developed Maxim's approach, but I learned this from Maxim paper and didn't read a lot of other papers. Okay, so let me explain. So what?
The result is what?
The result that this formula defines a non-commutative Poisson structure on projective space, Cpn-1. Yes, and
I don't know whether the quantum version makes.
I don't know what is a quantum version in a non-commutative case. It's a very good question. It's some structure which gives you quantization of all corresponding Poisson structures on these increasing spaces of representations of matrix of the algebra, but I don't know any.
The equation properties can do equations, and you don't know, and also have no idea what it would be. Quantization of this Poisson algebra.
Yeah, this is what we. Yeah, it's a very interesting question, but we should start with understanding what quantization means in this case. Something which gives you quantization of all matrix. I don't know.
Actually, what is projective space for matrices?
I will explain. It's not for matrices. This I will explain.
It's a non-trivial point.
Yeah. I will explain this.
But if you just take this formula, so it does not satisfy Jacobian identity or what?
Okay, well, you want me to explain it now. Okay, good. Good. In this case, what does it mean? It's actually similar to this. You can modify it, but not only by this. You can put xi here. It will be another identity. And similarly here and here. According to Maxim, this equal to when you put xi here, but anyway, you must do this. And then Poisson identity should, Jacobi identity should be equal to 0 again modulo such equations. This is what it means. But there is also a way how you can apply this formula to homogeneous functions. I will explain this. There is a version of homogeneous functions, and this is a homogeneous two-vector field. There is a version of quite natural. So in fact, I will explain this. So for non-commutative case, you can introduce projective space in two ways, in affine coordinates and in homogeneous coordinates. It's quite similar to usual case. Well, everything, okay? And you can apply it to homogeneous functions and also have homogeneous function.
But for just associative algebra, when you deal with dxi, you have to define it. But things like the Euler relation, use commutation.
I will explain. You need to choose. So it is generated by x I in the power of -1 x j. You need to choose from which side you have, because you have. Sorry, one moment. You can assume homogeneity condition. A is non-homogeneous auxiliary variable. If you choose this side, if you multiply from this side, you need to take this. If you multiply it from this side, you just swap it.
But because you will consider only conjugation invariant function, it won't matter which side you choose.
Yes, for homogeneous coordinates, it doesn't matter, yeah, in homogeneous coordinates. But here, yeah. And this is also homogeneous. Homogeneous differential geometric structures are those which are also invariant with respect to this. Okay? So it's very similar to usual case. Okay? Yeah? Any questions? So I'm not sure that everybody remember very well Maxim's formalism. Yeah? You remember probably? Not very well. Anyway, my aim now is to review this. Okay? At least review my understanding of this. Those part which is important for my purposes. Yeah, it's really crossroad of centuries because Maxim invented this in previous century, and Boris Feikin and I invented this algebra also in previous centuries, but this non-commutative version was invented in this century. In this sense, it is on crossroad, yeah. So first, let me review affine case. Affine case, which you for sure you know this. Your affine case. So I'm going to review non-commutative polyvector fields, to be precise, for affine space. So for affine space, you have, let me introduce the following notations. A, just a free algebra. So I work over complex numbers. It's kind of traditional mathematical physics. This is a notation for free algebra with n generators, x1, xn. So bases here are just all words from this alphabet. Now, and if I understand well, as far as I understand, this is a kind of ring, coordinate ring of affine space. Well, it's my understanding. Okay, anyway. Now let me introduce F, which is commutant of A. Quotient of A by all commutators, by a vector space which is spanned by commutators. Not ideal, just vector space. So this is not algebra, this is just a vector space. And according to my understanding of Maxim's framework, this is a space of functions on non-commutative affine space. Okay?
Maybe generators of space.
Maybe, but well, anyway. So this is vector space, not algebra, with basis of cyclic of such words up to cyclic permutations. Okay? Basis of here. So I have, for example, x1, x2, x3 equal to x3, x1, x2 not equal to x2, x1, x3 in F. Yeah. Okay, good. And let me denote by trace natural projection from A to F. This I denote by trace, by obvious reasons. Trace behaves similarly. Okay? So ring of coordinate rings, ring of function, at least in my head it is like this.
It is not commutator, it is ideal generated by...
It is not ideal, it is a vector space. Vector space. So it is not an algebra. Not algebra. Algebra, not algebra. Okay? Not algebra, algebra. Yeah? Okay? Good. Well, now what the next thing which I need to explain, and this is probably most kind of crucial step in understanding of this, because after that, everything which will be really very similar to usual case. I need to explain what is a vector field in non-commutative case. Okay, so let me explain what is a vector field. So now let me omit non-commutative, because everything will be non-commutative now. So in usual case, vector field is a derivation of algebra of functions. Yeah. So vector field is, but unfortunately this is not algebra, so I cannot say what is derivation. But so at least it is a linear map say nu from F to F. Vector field, at least we know that it should be a linear map of functions, which is this. But I cannot say that is a derivation because it is not an algebra. It cannot have derivations. But then I'm forced to say that it must be lifted to a derivation of A. So which, so such that, say, such that they exist
Just said, but I thought that partial derivatives, for example, are no longer cyclic.
We will come to this. Yeah. This I will explain. Such that there exists a derivation let me denote it by d nu from A to itself. Well, again, such that, well, of course, we should have the following commutative diagonal. Well, A to A, this is D nu, I have F to F, which is nu, and here I have trace. So, a vector field is such a map which can be lifted to a derivation of A. Simply speaking, it is like this. Okay? That's all. In this case, in commutative case, A is equal to F. But in this case, A is not equal to F, but we kind of deform. So now we cannot require that is a derivation, but we require that it can be lifted to derivation. Any questions about this? Questions? Trace is going from A to F. You consider trace just. It's a definition. It's a definition.
No, it's a projection. Why do you call it a trace?
Because trace satisfies the same identities, and also it's a kind of universal trace. Kind of universal trace. If you take arbitrary functional on F and
I would have said that the trace is defined on A because the trace of commutative is 0 on F. So trace should go from F to somewhere.
Yeah, it's
trace is well defined on F. F is the origin of the trace, not the image. I'm very confused about the notation.
Yeah, notation is confusing.
I'm sorry. The trace is well defined on F because
it is a kind of universal trace. If you take arbitrary functional on F, then composition will be a kind of trace of a representation. It's kind of trace of possible representations of A. No. Something like this. Sorry?
You know TR projection.
yeah, TR is PR.
Okay, yeah.
Sorry, but I cannot switch now to another notation. I'm sorry about this. Yeah. Yeah. Anyway, sorry about this, but it's different. Yeah. Yeah, I hope you can live with it. Yeah. Good. So, first lemma, which is easy, I would say. Nu, mu are vector fields. I have two vector fields. Then commutator, nu, mu. Commutator in usual sense, like commutator of linear operators, is a vector field. Okay? Well, proof is very easy, yeah. D nu mu is equal to commutator of d nu d mu. This is the proof.
The way you've written it, there is no d nu.
As there exists d nu.
Exactly, so there are many d nus. It's not, or is it unique?
No,
In this case, I believe that is unique.
No, it's
not unique. Not unique?
Up to inner automorphism, up to inner derivation.
Maybe, but anyway, I fix.
The field that you wrote,
Yeah.
or does it include d nu?
But I don't need. They exist. They exist.
Just exist.
They exist.
Then I don't understand this formula because maybe you take a different d nu.
Well, they exist. If I choose representative here and here, then this is a good representative.
This is a definition.
This is a definition, yeah. Definition. Well, that's proof and definition of. So I need to prove that given that nu and mu can be lifted like this, I need to find a lifting for this. This lifting is given by this formula. It's a proof. Proof? Yeah, it's not physical proof.
One can classify the non-uniqueness of the liftings, that is derivations which.
But this is not my aim to do this. It's just a definition. Okay? Good. Well, given this, let me explain what is polyvector field. It's actually now all other definitions are very, very similar to usual case. So what is a polyvector field? Which I need for definition of non-commutative Poisson structure. So definition is actually the same as in usual case. So like P vector field nu. Well, it is a skew-symmetric polylinear mapping from f in the power of p to f. It should be polylinear skew-symmetric and nu is a vector field, with respect to each variable when we fix other variables. With respect okay, so if I take nu of say a1, a2, ap, so nu is a function in p variables where a are elements of f and with value in f. It should be skew-symmetric. When I change variables, it's skew-symmetric, and it should be polylinear, linear with respect to each variable, and it also should be a vector field with respect to each variable. If I fix all variables but one, it is a vector field with respect to this variable. It's just as the same as in usual case. In the usual case, commutative case, as soon as we know what is a vector field, we can define p vector field in this way. Okay? Nothing new. Yeah? Questions? Complaints? Yeah? Everybody good? Okay. Complain? Yeah? Okay, now let me explain. Again, now there are several definitions which are really the same. Let me make it here. Just, I don't know how to read it. Schouten brackets. Schouten brackets, yeah? Thank you, Maxim. So, Schouten brackets. This I need to rewrite.
Schouten-Nienhuis.
That's a challenge. It will take all the remaining time.
Schouten brackets.
Schouten.
Schouten. Ah, natürlich. Schouten. Okay, let me just call it brackets. To simply. Well, so definition, in this case, definition and proof that it is a bracket is exactly the same as in usual case, just exactly. So let me just sketch. So nu is p vector field, mu is say q vector field, Yeah, Ni is a p vector field, and mu is a p vector field, mu is a q vector field. Then I can write a formula for p plus q minus 1 vector field. Let me just sketch. Yeah, so a definition. Bracket between mu and nu. It should be p plus q minus 1 vector field. So it should depend on a1, ap plus q minus 1. By definition, which you can read in Wikipedia, actually, I should take nu of mu a1 aq. Then I should put everything else, aq plus 1 ap plus q minus 1. So I can try to make composition. Yeah, take mu of its arguments and put all other arguments. And now I make alternation. Let me just sketch it by saying that I make alternation by arguments and by nu and mu. Alternations with appropriate sign, which I don't. The same, yeah, I make alternation of this, which means that I make swap of variables and appropriate sign. So alternation by a1.
So you have n factorial terms.
A bit less, because when I make swap this, it is q symmetric, so I don't. Kind of p plus q minus 1 factorial by. But all this, let me. You can find formula in Wikipedia. Okay. So alternation by a1, ap plus q minus 1, and also alternation by mu and nu. I should swap also mu and nu with appropriate sign, which I don't remember.
Do you divide based on factorial or not?
Sorry?
Do you divide so there are different?
I should. There is some coefficient which I just hide in this sign, in this symbol alt, and which I don't remember, of course. Probably it will be p plus q minus 1 factorial over p factorial q factorial, something like this. I don't know at the moment. But you can see it. Formula in Wikipedia. It is exactly the same formula. Yeah, as in commutative case. Okay? Well, so claim is if nu and mu are p and q vector fields in non-commutative situations, this is also p plus q minus 1 vector field, and proof is exactly the same as in usual case. So let me don't give it.
So what will you
exactly the same.
So what we use, we have vector space and some algebra acting on this vector space. That's it,
yeah. I use this claim for vector field, and basically that's all. Yeah. But proof is exactly the same as so I don't need to write it down. Okay? Well, now we are ready to define what is a non-commutative Poisson structure. Yeah, probably it's obvious. Let me do it here. Let me do it here. Well, probably you already guess what is a non-commutative Poisson structure. Yeah, again, the same definition as usual. So kind of main definition. Nu Fg is non-commutative Poisson structure if nu is a two-vector field and this bracket nu with nu is equal to 0. Of course, this is non-trivial. It is not identically 0. It is a kind of super skew symmetric. The same. This is actually a Jacobi identity for this vector field. Okay? Well, very good. Now I have time to explain what we should do for projective space. If you don't, that's all what I want to say. No, sorry. No. Now I need to explain. I need to explain how to give actually formulas for vector fields and polyvector fields. Let me do, sorry, just completely forget about this. So all this is good, yeah, but we need to write formulas. Let me explain how to write formulas. Well, let me start with vector field. Well, let me do it here. Yeah. Suppose that I want to write a formula to define some concrete vector field. Well, in usual case, when you define vector fields, you need partial derivatives. So let me explain what is a partial derivative in this case. So in this case, partial derivatives d by d xi are actually mappings from F to A. Okay? From functions to free algebra. Well, there is a scientific way to define it using non-commutative differential forms, but let me, because I don't have a lot of time, let me just explain it by example and by explanation. So what is it? Suppose I want to compute d by dx2, say x1, x2, x3, x2, x4. So I prefer to explain it by example, okay, because we don't have a lot of time. So what should I do? I want to compute this is a cyclic word, so here I can make cyclic permutations. And I should look up for x2. I compute partial derivative by x2. So one x2, another x2. With each x2, I do the following. I make cyclic permutation to put it in the beginning. And then I just delete it. So in this, if I take this, I have actually x3, x2, x4, x1. Yeah. Yeah, I put x1 here and delete this x2. Plus, now I have another x2, so I just put x4 here. It doesn't matter if I put x2 in the beginning or in the end, because the result will be the same. So I will have x4, x1, x2, x3. Okay? So if I don't have x2, it is 0. If I have x2, for each x2, I make cyclic permutations to put this x2 in the beginning or in the end, and then I delete this x2. Okay, and this can be expanded. Later I will add inverse of generators. It also can be done in this case, but let me explain this. Okay? Well, so it's so this is a cyclic word, but this is just element of free algebra, because when I make cyclic permutation to put this x2 in the beginning, I kind of fix ordering of these letters. Okay? And now it turns out that any vector field, so any vector field can be written in a form nu applied to f is equal to trace, sorry about this notation, of a1 df by dx1 plus plus an df by dxn, where a1, an are elements of A. Okay? This is a claim. I don't have time. Probably it's a good exercise for those who doesn't know this. Any vector field can be specified by choosing elements from A, kind of coefficients, and then it can be written in this way. For different A, it will be different as far as I maybe no, not. Anyway, at least for some, it will be. At least I claim that any vector field can be written in this way. Yeah, A1 is up to choosing of this derivation. Yeah, because A1 is d nu of x1 if you change d nu, then a1 will be will be. But anyway, any can be written this way. Okay? Well, in this case it is good because roughly speaking, vector field is defined by the same formula. I just must write this trace here. I think it is unique, but I'm not in position to argue. Well, anyway, it's not, even if it is not unique, I think it is unique.
It's second axis and one from you.
Yeah, but I already. So unique?
Unique.
Oh. And derivation is also unique.
No.
No, the inner derivation always goes.
Okay. Anyway, now how to write? Let me now explain how to write two vector field. Let me, and for p vector field it will be very similar. So let me do it. Well, maybe I should take this. Oops. So let me write a formula for two vector fields. And you will see that for two vector fields and for high vector fields, turns out that you need much more data to define non-commutative polyvector fields. So two vector field, any two vector field can be written as nu f and g. So I should take trace, and now I should take a with some indices. Let me write indices later. I have df by d x xi, b dg by d xj, and here I have sum, and here I have I, j, r, and here I also have I, j, and r, and here I and j from 1 till n, but r could be from 1 till some very large number in principle, capital N. Okay? So potentially you have as many data, and of course a ij r and b ij r are elements of A, and they are really not unique. I will explain. Kind of not unique in manifest. It's clear for me that it's not unique. Okay, so I make summation. So first of all, I have kind of usual part. I have a ij, bij, I have partial derivative of f, partial derivative of g. Yeah, but in non-commutative case, in commutative case, we can just collect df by dxi, dg by dxj, and have just kind of n minus 1 over 2 terms. But in this case, we cannot swap. We cannot collect. Yeah, so this a and b are kind of elements of free algebra, which depends on these indices I and j, but there is additional index, which can run as large set as we want. Okay, but because we cannot collect this. Okay? Is it clear?
The antisymmetry is not.
Yes, antisymmetries give some constraint for A and B, which I cannot write down at the moment. And should be antisymmetry, it gives constraint, because for antisymmetry I can make cyclic permutation, this. Yeah, but there is the following subtlety here. In addition to that, we can kind of expand and collect a little bit. We have the following identity. We have the following identity, which was found by Maxim. For arbitrary function, we have the sum commutator df by dx I from 1 to n is equal to 0. Sum of for arbitrary element of free algebra. Oh, sorry, it's f from f. Yeah, if we take commutator in free algebra of xi and partial derivative and then sum up, it is identically 0. Not hard to prove, but I don't.
Well, I think you should read it in some paper by Greenfield.
Maybe. I saw it in your papers. Sorry. And using this, you can modify this in a lot of ways. Yeah, you can take, for example, from here you can take x1, from here you can take df by dx1, and then you can find it from here and replace. Okay?
Actually, I think the same for vector fields as you defined is also the same.
No, because here by cyclic permutation I can put everything in the beginning. And this here we mix when x in the beginning or in the end. So for vector field we cannot modify using this. But for polyvector field, for example, for two vector field we can. Okay? Okay? And similarly for p vector field, it's similar, just more term, more longer product. Well, now I have 4 minutes. Let me very, very briefly explain what we should do for projective case. I have 4 minutes, yeah?
No, in fact, it was a mistake. I think if for vector fields, when AI is commutator of some g with xi for each I, then the whole thing will be trivial.
But, well, let's discuss it later. I don't know at the moment, okay? Naively, I think that you can put everything in the beginning, and that's it. But let's discuss it later, yeah? Because I want to have just tell a few words, yeah, for projective case. Okay. So in projective case, let me do it here. You need to expand everything. Wake up, everybody. So for projective case, you just, well, it's not a good idea to inverse everything. It's enough for my purposes to inverse only generators. So for projective case, I take a hat, which is free algebra, kind of free Laurent polynomials. x1 in the power plus minus 1, oops, free. xn in the power plus or minus 1. So f is just again commutant. Okay. Now we can introduce auxiliary non-commutative parameter a and make the following transformation. Xi goes to a xi. And now differential geometric objects, for example, functions, vector fields, polyvector fields are called homogeneous if they are invariant with respect to this. Okay, for example, x I in the power of minus 1 xj. This is invariant. And using this, you can introduce affine coordinates on projective space, kind of analog of affine coordinates. When you fix this, it will be analog of affine coordinates. There are transformations from one coordinate chart to another coordinate chart. Also, two form which I wrote with x by derivative by x by derivative, it is also homogeneous with respect to this. Yeah, and then we can introduce all everything as in usual case. Just say that we have affine coordinates when we fix denominator. We have homogeneous coordinates, and homogeneous coordinates, everything should be homogeneous, yeah, if you want to define it on projective space, and so on. So I think that I already formulated main result in this, so probably I can stop now and some questions. Yeah, thank you.
Maybe you forgot to say that it leads to actual Poisson brackets on some, like you replace by matrices after conjugation, general point, and projective space collection of matrices may be invertible.
And in projective case, you also should make quotient by this for A is a matrix. Yeah.
One can consider just one-dimensional local systems with non-commutative on a sphere with n plus 1 points. It's the same thing.
But then you can ask about quantization if you have a
Yeah, I already asked this, but I cannot find answer. Yeah, it's very interesting because first we need to understand which structure will give you quantization. Some structure in terms of non-commutative variables, which simultaneously give you quantization of all Poisson structures on this matrix, of these quotients of matrices for arbitrary size. I cannot invent this at some.
Yeah, I have a question. I didn't understand something basic. You wrote some formula for this Poisson bracket, and you said that it defines the projective bracket.
Yes.
But why does it map homogeneous functions to homogeneous?
It is possible to prove it. You should prove that it is invariant with respect to this. To prove this, I didn't have time to say that these non-commutative things are actually geometric objects. You can make change of coordinates. To make change of coordinates, you need another type of partial derivatives. And using another kind of partial derivatives, you can write a chain rule for Maxim's partial derivatives. And then you can make change of variables. In particular, you can go to to affine coordinates and compute your bracket in terms of affine coordinates by fix this equal to 1, for example. And it will give you really non-commutative polynomial Poisson bracket for affine coordinates for arbitrary fixed I.
What is this A? Is xi going to
A is auxiliary non-commutative variable. You just make, in your formula, you make this transformation assuming that A is a constant non-commutative variable, and you require that your object is invariant with respect to this transformation, that A disappears. Yeah, but you need to know how to make change of variables, which I didn't say, but it is written, for example, in our paper, and it wasn't invited. I don't know who, Maxim probably invented this. Okay? Yeah?
More questions?
Can you say something about symplectic leaves on this representation or not?
No. Even for 2 by 2 matrices, I didn't spend a lot of time on this, but just if you spend 1 day, at least when I spent 1 day, or maybe several hours. But it is a very interesting problem. So for matrices of arbitrary size, as I told, under this and conjugation, you have just usual Poisson structure. It would be very interesting to understand, maybe geometrically, structure of symplectic leaves. Well, I think that Maxim probably have suggestion, because Maxim, it's time to talk about Maxim, yeah? Maxim, when I told Maxim about our result, he told me the following. Well, it's trivial, because your Poisson structures with Fagan are Poisson structures on some moduli space. But if you have moduli space, it's trivial to make kind of non-commutative version. It's just trivial results. Yes. So then you probably know how to compute symplectic leaves. Yeah, so it's a question to Maxim.
Yeah, so all questions to Maxim.
More questions? If no, let's think.
And sorry.